Okay, so we're back with episode 8. Okay, so we're back with episode 8. In this video, we're going to be going over a Euclidean question that does not revolve around our prop theorem, midpoint theorem, etc. Because, obviously, under the Euclidean section, you don't only get those type of questions. And obviously, we're trying to go through the different variations of Euclidean questions that will be asked in your exam just to make sure you guys are prepared. So, by the way, guys, don't forget to actually hit the notification bell so that you know or that you're reminded to check these videos every day. But other than that, let's get started. So, we have in the diagram we have A, B, C, D. It's a cyclic quad. Now, the minute they've told you that a cyclic quad is present in some questions, they aren't going to mention this. But if they do mention anything about a cyclic quad being present, you need to write down three of the theorems that remind us of cyclic quad. We think of opposite angles of a cyclic quad are equal to opposite angles of a cyclic quad are equal to 180 degrees. We think of that. What else do we think of, guys? We think of angles in the same segment. What else do we think of, guys? We think of exterior angle of a cyclic quad. So now let's first start off with opposite angles of a cyclic quad are supplementary. They're equal to 180 degrees. So let's just highlight A, B, C. Okay. So I'm just going to, so by the way, guys, we actually have numerical values in this cyclic quad. So we're probably going to have to use this theorem. We're obviously not going to annotate it onto our diagram. But if you feel like you're going to forget about using it, then just go back and annotate it. Just annotate this to each and every single side that is on the circumference of the circle. Go back and annotate, supplement your opposite, anything that's going to help you remember opposite, just write it over there. Opposite, yeah. Just write it, right? You can even just use an O, you can use O as a symbol that's going to help you remember opposite angles of a cyclic quad are equal to 180 degrees, just in case we need to use it. Let's go on to angles in the same segment. Now, with angles in the same segment, you need to look for a little bow tie shape with each point, with each part of the bow tie, with each and every single side of the bow tie touching the circumference of the circle, which all four sides touching the circumference of the circle. Now, in this case, we can't really spot or identify a bow tie shape. We just have, like, different lines that kind of are diagonal to each other. So we can't really identify that. So that's not going to work. Let's look for exterior angle of a cyclic quad. Now, a lot of students might think that, hey, this should, this should, um, this should fall under the exterior of cyclic quad theorem. This should be a part of it, which is not the case, guys. Remember, you have to have a very straight line that is literally at the exterior of the cyclic quad, so that it has to look like that. Then maybe if you had an angle with that over there, then yes, that would be a part of your exterior angle of the cyclic quad theorem. Or even if you had like a straight line over here, or if you had a straight line over here, and then the angle kind of, it starts from this point and ends all the way over here to this line. Or if it was on this side, then it cannot be skewed. This is obviously a tangent line, by the way, guys, not a normal line segment. Okay, so if it was like that, then yes, that is when exterior angle of a cyclic quad would actually be applicable. But unfortunately, in this question, it is not applicable. Okay, so yeah, this is not applicable, so we also cannot use that. It's not valid. So let's continue on. Now, they tell us that G is a point in AD such that BG is parallel to CD. Now, before we continue on, we just want to write down a few of the rules that we are reminded of when we have two parallel lines. We think of alternating angles, we think of cointerior angles, and we think of corresponding angles. Now, let's see if any of these rules are applicable to this question. So now, let's first start off by highlighting our parallel lines. Okay, we're gonna first start off by highlighting our parallel lines. Okay, so now let's first start off with alternating angles. So the alternating angles, they would usually be a transversal connecting the two parallel lines. They would usually be like a little diagonal line connecting the two parallel lines to one another, and the angles that are in that alternating position are going to equal to each other. So here we can clearly see that B2 will equal to D1 because of alternating angles. So what I'm going to do is I'm just going to mark that off as being equal to 30 degrees. You also want to check if it applies on your left hand side. So I'm gonna try and look for another Z shape from my left hand side. No, it doesn't apply to my left hand side. So no, this is the only part of the diagram where I see that Z shape. So we're gonna continue on and see if co-interior angles apply. Well, we usually use cointerior angles to calculate the value of, like, a numerical value of an angle. So we're just going to keep that in mind. You never know, we might need it. Okay. And then let's go into corresponding angles. This is a rule that a lot of students do forget about. Now, for corresponding angles, you have to identify an angle that comes before one parallel line and another angle that comes after the other parallel line. Great example of this would be G2. G2 comes right before BG, which is a parallel line. So G2 is going to equal to D2 plus D1 plus D1 because of corresponding. So you need to make sure that the angle that comes before that parallel line, firstly, there has to be like another line that supports the two parallel lines. Like you can see AD supports the two parallel lines, and then G2 comes before the BG line, and it equals to the other parallel line, sorry, the other angle that comes after the other parallel line, which is D2 plus D1. Not just D2, don't make the mistake, guys. The angle has to come from the line that supports the two alternating angles and all the way back down to the parallel line, which is DC. So it's D2 plus D1. And yeah, so that is all I can see when it comes to corresponding angles. Okay, so now let's continue on, guys. They tell us that ECF is a tangent line. Now we're also going to write down a few of the rules that we're reminded of when we think of tangent lines, guys. So we think of tangents at the same from the same point. We think of the rule. We think of tan chord. I'm just going to write T, C for tan chord. We think of tangent perpendicular to radius. Now, let's first start off with tan chord. Now, how does this rule work? What you have to do is first have to highlight your tangent line, which is ECF, and then you have to identify your chord. Just separate it for yourself, break down the question. It's tan chord. Identify your tangent, identify your chord. So the chord that is close to our tangent, in this case, would be DC. Now the angle between DC and the tangent line, by the way, guys, in this case, we're looking at EC, which is a part of the tangent. You need to look at the angle between those two lines. So the angle that's between those two lines would be C1. You can clearly see that that is C1. Okay, so C1 will then be equal to the angle that the chord subtends. Now, what does it mean to subtend? Now, this is very easy to remember. So I want you to think of a line. By the way, think of a line. In this case, we're looking at DC. To subtend means that that line holds an angle all the way to the other end of the circle until it reaches the circumference. Okay, so if we have line DC, for instance, the angle that it subtends would be this line right over here. I'm going to label this name because it holds the angle so to the point where it touches the circumference of the circle on the other end. Okay, so we're going to go back and trace the lines that stem from DC. Let's start off with D. Trace it, trace it, trace it, trace it, trace it, trace it. It ends over here. Do the exact same thing to the other part of the chord. Trace it, trace it, trace it, trace it, trace it. It ends all the way over here. So we definitely know that DC subtends B1, meaning that C1 will equal to B1 because of the tan chord here. Now let's look at the other part of the line as well. We have CF. Identify, we're going to obviously be looking at both sides of the tangent. So we already started off with CE. We're going to go on to CF. Okay, so now let's look at CF. Identify your tangent, okay, which is obviously CF. Identify your chord. In this case, our chord is going to be BC. Then identify the angle between BC and CF in this case. Okay, the angle between those two would be C3. Identify the angle that BC subtends. Just take your pencil and trace the lines that stems from BC. Trace it, trace it, trace it, trace it to the other end. It ends over here. Do the exact same thing on the other side. Trace it, trace it, trace it, trace it, trace it. It ends over here. So we do know that BC subtends D1, meaning that C3 is going to equal to D1. So I'm going to mark that off, but I'm actually just going to label C3 as being equal to 30 degrees because we can clearly see that D3 equals to 30 degrees. I'm just going to go back, not D3, sorry, D1. I'm just going to mark them off as being equal to each other. Okay, so now guys, let's go on to tangent perpendicular to radius. Now this theorem is immediately not going to work, guys, because we don't even have a radius. How do we know that? If we do not have a center, if we do not have a center that is a part of our diagram, we definitely cannot have a radius. A radius is literally a line that stems from the center to the circumference of the circle. So if you don't have a center, then you definitely can't have a radius. Now let's start off with tangents from the same point. Now in order for this theorem to work, you need two tangents You only have one tangent, so that's definitely not going to work. It is not applicable to this question. So now let's continue on. Okay, so that's all the important information that we have. Now let's continue to 8.1.1. Calculate the degrees is the size of D1. And the great thing about annotating your diagram is literally before you even start answering the questions, you already have your answers. Okay, so it's so important to annotate your diagram and also use color coordinating. So when I use corresponding colors, so if you think two angles are equal to each other, just mark them off using the same color. And also, before we continue, guys, I just want to remind you that we are hosting daily sessions literally every single day for both grade 11s and grade 12s in preparation for your final exams that are coming in a few weeks, guys. So if you had a level 3, level 4, level 5, then if you join and you literally dedicate yourself to the process, because we go through commonly off exam questions, guys, you cannot go wrong. We're going to be going over the questions that will be in your exam, guys. Okay, we're going to be going through the questions that will be in your exam. You're going to be receiving a binge series for the questions that we obviously won't be able to complete within the sessions, because our sessions are 2 hours long each and every single day, just to make sure you guys get that practice. Okay, and we've conducted so much research in actually compiling this file to make sure we find the questions that have a very high chance of being in your exam. Okay, so if you want to join, guys, if you'd like more information regarding the how it works, the prices, everything, then just make sure to send an email. The email's in the description. But other than that, let's continue. Now let's go on to 8.1.1. Calculate the size of D1. D1, we've marked off D1 as being equal to B2, remember, because of alternating angles. Okay, so that was pretty simple. Okay, we know that D1 is equal to B2. We've literally marked them off in red. Literally, D1 is equal to B2 because of alternating angles, and we know B2 is equal to 30 degrees. So that was a very easy. You're gonna say that D1 equals to B2, which equals to 30 degrees, alternating angles, and then you have to state which two lines are parallel to each other, causing that allows us to validate our answer. You're gonna say because DC is parallel to GB. Let's continue on. I just want to mark that off onto your diagram. 8.1.2, calculate the value of B1. Now let's look. Remember, guys, we've marked off B1 with gray. We've also marked off C1 with gray, and we said that they're equal to each other because of tan chord. So you want to say B1 equals to C1, which equals to 60 degrees because of our tan chord theorem. So you're gonna say B1 equals to C1, which equals to 60, tan chord theorem. Okay. Now, do you see how fast we're moving? It's so easy, guys. Now let's go on to C2. Question 8.1.3, we have to calculate the value of C2. Now, this is so important, guys. We haven't marked C2 off as being equal to any other angle using our generic Euclidean theorems. We didn't use tan chord. We didn't use alternating angles. We didn't use, any of those generic Euclidean theorems. So, if we haven't marked off an angle that isn't directly equal to another angle using our generic theorems, I want you guys to think of the other geometrical theorems that we learned all the way back in grade 9. Sum of angles of a triangle. I want you to think of exterior angle of a triangle. I want you to think of vertically opposite, and I want you to think of angles on a straight line. I want you guys to make a little list for yourself so you don't forget. Now, remember, we already said that B1 equals to 60. I want you guys to go back and mark that off. The minute you see, in this case, it's so straightforward, it's so easy. You could actually also use angles on a straight line. C1 plus C2 plus C3, they're all on a straight line, and we know what the values of C1 and C3 are, so we could use angles on a straight line, or you could easily just use sum of angles of a triangle. If you see an angle that is a part of a triangle and you already know what the other two angles values are equal to, just use sum of angles of a triangle. It's so easy. We're gonna see D1, which is 30 degrees, plus B1, which is 60 degrees, and then plus C2, which we're trying to get to. And then you're gonna equate that. Okay, so then you're gonna go back and equate that to 180. So what is 30 plus 60, guys? It is 90. You take the 90, subtract it from the 180, meaning C2 is going to be equal to 90 degrees. And you have to state this properly. You're just gonna say C2 equals to 90 degrees, sum of angles in a triangle. But let me tell you something, guys. You just need to show all your steps. Okay, you need to indicate all your steps. Don't just write off all the answers. You need to just show the memo, show the marker that, hey, you actually got this answer using this method. Okay, so you want to mark it off as being 90 degrees. Always mark it off after you're done. So now with the next question, we have to calculate the value of DAB. Now, AB would be this angle right over here. Now remember what we did right in the beginning when we were annotating. We annotated each and every single angle on the circumference of the circle that was a part of our cyclic quad as opposite because we did not want to forget to use opposite angles of a cyclic quad just in case we need to calculate what their values are. Now that's exactly what I'm thinking. The minute I see an angle that is a part of a cyclic quad, I always think of using opposite angles of a cyclic quad, especially because we know what the value opposite that angle, opposite from that angle. We already know what its value is. Easily, we're going to use opposite angles in cyclic quad. Already, we already know, guys. So you're going to go back and say that A plus C2, which is 100, which is 90 degrees, equals to 180. And your reason is going to be opposite angles of a cyclic quad. Take it over onto the other side, you're going to get an answer of 90 degrees. So you want to say DAB plus C2 equals to 180 degrees. C2 is equal to 90 degrees. And over here, they made the mistake of not giving a reason. Your reason has to be opposite angles of a cyclic quad. And for the last question 8.2, is BD a diameter? Now, what makes an angle a what makes a line a diameter? So we're looking at BD. They're asking if BD is a diameter. Remember, we already found out that A was equal to 90 degrees. Okay. Now, is BD a diameter? Let's just go back and highlight BD. So what makes a line a diameter? What makes a line a diameter is if it subtends a 90-degree angle. So now let's look at the angles that BD subtends. We're going to start off by taking our pencil and tracing the lines all the way to the other end of the circumference of the circle. So we trace it, trace it, trace it, trace it, trace it, trace it, it ends over there. Go back to the other end of the diameter, trace it, trace it, trace it, trace it, it ends over there. We know that it subtends C2 and C2 is 90 degrees, meaning it is actually a diameter because it subtends a 90-degree angle. Now we can even do this on the other side. Take your pencil, trace the lines all the way up to the other end of the circumference of the circle. Trace it, trace it, trace it, trace it, trace it, trace it. It ends over here. Do the exact same thing. Take your pencil, trace the lines from the other end of the diameter, trace it, trace it, trace it, trace it, trace it. It ends over there, and it literally subtends 90-degree angles on both sides of the triangle. So therefore, we can confirm that BD is indeed a diameter. Now, we have to give a proper reason, guys. We need to use the reasons that we've been given. There are literally valid reasons. That you'll get marked for in matric. You can't just state any reason. You have to say converse angle in a semicircle. Why is it converse? Why is the opposite? Because usually you use angles in a semicircle when we're trying to prove that an angle is 90 degrees because it's a diameter. But in this case, we're trying to prove that it's a diameter. When we're trying to prove that a line is a diameter because it subtends a 90-degree angle, the reason you need to use this converse angle in a semicircle. Okay, guys, so we've come to the end of the video. Hopefully this video was helpful. Make sure to watch the next video. Make sure you hit the notification bell, guys. You're not going to miss these videos. You don't want to end up binge watching these videos days before your exam. So make sure you hit the notification bell. Make sure you check in every single day so you can watch. Other than that, we'll see you in the next video.